all hear me?
Yes, madam.
Yes,
Yes,
madam.
madam.
Yes, madam.
Okay, there is a heavy rain. So sometimes my voice will not be clear, right? So is it clear?
Yes, madam.
Yes, madam.
Okay. So today we have scheduled to do the first tutorial class, but unfortunately the your tutor, she has a current failure, so I thought to conduct the lecture today, right? So we were discussing about the random variables, right? Random variables. We define what is a random variable, and then we discussed that we can divide the random variables into two parts as discrete and continuous, right? When the event of sample space is a discrete value, then the random variable or the function we define on the sample space is a discrete random variable. If the outcome of the sample space is continuous, then the function defined on the sample space is called a continuous random variable, right? So we discussed how to write the probability distributions for both cases, discrete and continuous, and then the cumulative function for both cases, discrete and continuous, right? So for the probability distribution, discrete case, we just say it as a probability distribution, but in continuous case, we said it as a density function, right? Density function. And the cumulative distribution, the cumulative one, it is the distribution function, right? It is the distribution function. So we learn how to obtain the cumulative or the distribution function when we given the probability distribution, right? So those are the things we discussed in last lecture session, and we discussed the problem, right? Can you remember? In the last moment, we discussed distribution function for continuous random variable examples, right? So there, the function was fx equals cx squared 0. This is for 0, x and 3. And 0 otherwise. Right? So we found C as 1/9 in the first part. And this is the part A. And for the part B, we found probability of x in between 1 and 2. Right? For that, we use this formula fx dx. Right? So we found the probability that is equals to 7/27. Okay. Then as part C, we found the distribution function. Right? The distribution function Fx. That is the cumulative distribution function. Cumulative distribution. So we can find the cumulative one from -infinity to x squared, or else we can just say Fx dx. Right? So according to that, we have found that the cumulative distribution or the distribution function is equals to x cubed 27. Right? And using this cumulative or the distribution function, we can find this probability as well. Without using this equation, we can find this, the part B, using the distribution function in the part C. Right? So how we can do that? That is, we can write probability x in between 1 and 2. So this is equals to probability of x less than 2 minus probability of x less than 1. Is that okay to write this? Since the capital Fx denote the cumulative probability, right? Cumulative probability, as you can remember. So we can write this one using this two probability values, right? So we know that this is F2. The probability up to the value 2. Right? And this is F1. So we have to just substitute this value 2 and 1 in the distribution function. So it is 2 to the power 3 over 27 minus here 1 to the power third 27. So it is 7/27. Okay. So we can use distribution function also to calculate these probability values. Okay. So the summary is, in the discrete probability distributions, we denote it using Fx we denote in discrete case Fx can be written as probability of x equals to x, simple x, right? and the cumulative one or the distribution function is the summation of fx and in continuous case the cumulative fx would be obtained using the integration of fx from x. Right? So discrete distribution එකකදී simple fx කියන්නේ x කියන point එකේදී probability එක, right? Generally simple fx කියන්නේ discrete distribution or discrete random variable එක එයාගේ probability distribution එක x කියන point එකේදී probability එක කියන තමයි fx function එකෙන් කියන්නේ. එතකොට capital fx කියන්නේ distribution function එකෙන් කියන්නේ x කියන point එකට එනකම් probability එක. x කියන point එකට එනකම් තියෙන cumulative probability එක. එතකොට අපි ගන්න එක summation වලින්, right? ඊට පස්සේ continuous case එකේදී අපිට exact point එකක් නෙවෙයි තියෙන්නේ. continuous variables වල අපිට infinite range එකක් තියෙනවානේ. So අපි range එකක් ගන්න එතනදී. ඒ range එකක් ගන්න නිසා තමයි අපි simple fx ලියන්නේ මෙන්න මේ විදිහට. එතනදී අපි කරන්නේ යම්කිසි points දෙකක් අතර, ඒ කියන්නේ range එකක් අතර probability එක. range එකක් අතර. In this example 1 to 2. එකේ ඉඳලා දෙක අතර probability එක. And the cumulative distribution එක කියලා කියන්නේ එහෙම නැත්නම් distribution function කියලා කියන්නේ continuous variable එක minus infinity ඉඳලා අපිට දෙන x කියන point එකකට වෙනකන් තියෙන cumulative probability එක. එතකොට අපිට එතනදී summation ගන්න බෑ. variable එක continuous නිසා. Therefore we use integration. Right? That is the basic thing here. So this last part I couldn't show you or include it into your note. So just write this one. I'll share a slide. So at this slide, at the end of your part 1 of the chapter 2, right? Can you see this slide?
Yes, ma'am.
Okay, if simple fx and capital Fx are the values of the probability density and the distribution function of capital X at simple x, then probability in between A and B can be written as Fb minus Fa for any real constants A and B with A is less than or equals to B. So this is in example, we discussed this thing, one, right? And if the derivative exists, we can transform the distribution function into the probability density using the derivatives, right? So we obtain capital Fx by integrating fx by x. So we can use the other way around to obtain density function, we can obtain the derivative of the cumulative or the probability distribution function by x. Right? Include this slide to the end of the first part of the random variables, right? Okay. Okay. So today we are going to discuss some important properties of random variables today. Expected value and variance, right? Expected value and variance. So first we discuss what is expected value, right? When we're discussing about the distributions, the most important two properties are expected values and variances. When we go to the probability distribution, the next chapter 3 and 4, continuous discrete probability distribution. When we discuss about a probability function, the most two important things are expected values and variance, right? In generally, we use mean as the expected value. So what is expected value of a random variable? So as you can see in this figure, for a statistical experiment, we have two approaches called a practical approach and a theoretical approach, right? So for an example, if we roll a coin 50 times, right? Then we can obtain some number of heads and some number of tails for a fair coin, right? If we actually do the experiment, we have some frequencies for the head and tail and a mean value as well. A mean value, right? And if we assign values for head and tail, we can have let's say rolling a die, right? Then for each side 1 to 6, there is a frequency value. If we roll a die 50 times, and also a mean value, average value, mean or average, right? But if we, without doing the experiment practically, we can obtain a theoretical approach. For a fair die, we know that for a fair die, it has an equal chance of obtaining any value from 1 to 6. Right? So there may be a theoretical probability for each and every number from 1 to 6. So without doing an experiment, we can obtain a theoretical approach and we can obtain an idea about the probability values for each number 1 to 6, and that is called expected value. Right? So we have two approaches. If we done the experiment actually or practically, there may be there is a frequency distribution, not actually probability value. Frequencies 1 this times, 2 occur, 2 has been occurred this times. Likewise, there is a frequency distribution, and we can obtain a mean value, average value. But without doing the experiment, we can do a theoretical approach using the probability values. That is called use the probability distribution, and there, instead of mean value, we use the term expected value. Expected. බලාපොරොත්තු වන value එක, not the actual value. Not the actual mean when we're doing the experimental really. So this is an expected value, right? So that is the concept of expected value, right? So if x is a discrete random variable and fx is the value of its probability distribution at x, the expected value of x is given by, so we denote the expected value using this notation EX, capital EX, right? That is the expected value, right? So it is the summation of all x into fx values. All x into fx values, right? Fx means the probability distribution. We denote this normally, we denote this by mu. Mu, it is the expected value of x, which is also called mean of the distribution. So it is the mean of the probability distribution, right? So in theoretical approach, we deal with the probability distributions, and the mean of the probability distribution is called as expected value, right? So this can also be written as expected values in xi pi's. Pi is the probability value in each point of x. Then it can be written as xi pi, right? If x is a discrete random variable with probability distribution fx, the expected value of the function gx is given by, so we can find the expected value of a function, not only a random variable x, we can find the expected value of a function as well, right? If we have a function gx, then instead of including x, we can include here the gx fx, right? If we want to find the expected value of the random variable, it is x fx. And if it is a function called gx, it is g f x, right? Okay. For an example, consider this. This is for discrete case, okay? So for an example, suppose we throw an unbiased die 120 times and record the result in a frequency distribution. So this is the experimental approach. We have done the experiment, and according to the experiment, we have obtained following frequency values. This is called a frequency distribution, right? 1 has obtained 15 times, 2 22 times, 3 23 times. Likewise, we have obtained the experimental results. So if we calculate the mean score, right? The mean score is obtained by sigma fx over sigma f, right? 1 into 15 plus 2 into 22, 3 into 23, 4 into 19. Likewise, then we can obtain the mean value. So it is 3.558 up to the 3 decimal places. Right? If we consider the theoretical approach, theoretical case, the probability distribution for the random variable x, where x is a number on the die, is as shown. So we know that if it is a fair die, probability of obtaining 1 is 1 over 6. Each number has equal chance of getting on, right? Then according to the expected value, if we calculate the expected value, so it is summation of x fx, right? So summation of x fx. So here x is 1 into its probability, 1 over 6, then plus the summation, since it is summation, 2 into its probability 1/6, 3 into its probability, 4 into its probability, 5 into its probability, and 6 into its probability. So it is 3.5. So this is the expected value I discussed in earlier, right? So this is how the expected value obtained. So expected value is based on the probability distribution. Mean is based on the real world experiment in experimental approach. Okay. Right. So wait. So this is for discrete case, right? Okay. There are some results under the expectations. So if we take the expected value of a constant, right? Expected value of a constant is the constant itself, right? Expected value of a constant is equals to the constant itself, right? So we can prove it. The expected value of A, so we can write it as summation of A into Px or the Fx. Then since A is a constant, we can take it out from the summation value, as in here. We can get A out, and we know that all x, for all x, the summation of the probability value equals to 1. For all x, the summation of all the probability values equals to 1. So the expected value of the constant is the constant itself, right? So the result 2, if x is a random variable, then expected value of the random variable multiplied by a constant, then we can get out the constant out. We can get the constant out like this. So if we prove it, expected value of Ax can be written as summation for all x, Ax, right? So අපිට expected value එක හොයන්න ඕන එක මොකක් වුණත් ඒක හැම වෙලේම මෙතෙන්ට දාන්න ඕනේ, right? So it's Ax into Px. So since A is a constant, we can get out A from the summation and xpx. So we know that xpx is the expected value of x. So it is A into expected value of x. And result 3, here A and B are constants. So if A and B are constants, expected value of Ax plus B can be written as this. So we can prove it as well. So summation of all x, we put Ax plus B here and Px, right? So we can write this as, since there is a plus sign, we can break into two parts as Axpx and Bpx. So we can get A out, and xpx is expected value of x, and again using the result 1, expected value of a constant is the constant itself, right? Okay, then the final result. If f1 and f2 are functions of the random variable x, then expected value of the summation of two functions can be written as the separate expected value of the two functions, EFX is F1x and EF2x. We can prove that also. So for all x, we can write here instead of x, F1x plus F2x into Px. And we can break into two parts as F1x Px and F2x Px. So F1x Px is the expected value of function x. Summation of F2x Px is the expected value of function F2. So those are the results we obtain using the expected value. Right? Is it clear? Any questions up to now? Any questions? Okay, I hope there is no, right? So look at this example. Two bags each contain 3 counters numbered from 1 to 3. So there are 2 bags. Each bag contains 3 counters. It has been numbered from 1 to 3. A counter is drawn randomly from each bag. Let random variable x represent the sum of 2 numbers on the counters. Calculate EX squared, E2x squared minus 6x plus 5. So we have to calculate these expected values. So what is the case? 2 bags each contains 3 counters numbered from 1 to 3, right? So a counter is drawn randomly from each bag. So do make open